So what we're going to be doing now is we're going to be talking about hypergeometric expectation. And much like binomial, a lot of the value in coming up with these formulas is that it makes the expectation calculations substantially easier. So what we're going to say is, for one trial, we're going to make an XPX table. So for one trial, X P of X, X P of X. So for one trial, we could have 0 successes or we could have 1 success. And the probability of succeeding is we have A successes over T things in total. So the probability of success is going to be A over T. And the probability of non-success, I guess, would be, well, whatever. It doesn't really matter because 0 times whatever it is 0, and 1 times A over T is A over T. So, and then we add these guys up. So the expected numbers of successes after one trial is going to be A over T. Now, I'm going to do something that I call, well, I've heard the term before. It's kind of like a hand-wavy explanation. So what a hand-wavy explanation is that it's not totally true, but then I wave my hands and I distract you and you just accept that it's mostly true. And then we'll go for that. So what the hand-wavy thing is going to be is that what's the probability that the second one will also be a success? So the probability the first one is a success is A over T. The probability of the second one being a success will be higher or lower depending on whether the first one was a success or not. However, and wave, on average, it's going to stay at A over T. So on average, the probability of success is going to stay A over T. So for 2 trials, the expected number of successes is going to be 2 times that. And for 3 trials, it's going to be 3 times that. And for n trials, then for n trials, the expected number of successes is going to be n times A over T. And that's going to be our expected number of successes for a hypergeometric distribution. Okay, let's do some more examples. So a box has candies, and we're going to say it has 4 reds, 5 blues, and 6 yellows. And so the first question is going to be, if we grab 5 candies at random, what is the probability that exactly 3 are yellow? So in this case, success is going to be, and you could pause it here before I actually give the answer. Try to do it yourself. Or at the very least, try to set up the things. So success is yellow. N equals 5. A equals 6. T equals 4 plus 5 plus 6 is 15. And we're looking for 3 successes, right? There's 6 successes because we said that success was yellow. So then the probability that x equals 3 is going to be 6 choose 3 times that minus that is 9 choose 2 over 15 choose 5. 6 choose 3 times 9 choose 2 divided by 15 choose 5 is 23.9, so 24%. Which is 24.0%. Okay, that wasn't very exciting of a question. So B. what is the expected number of red candies if we pull 3 from the box? The definition of success has changed here. It used to be yellow. Now the definition of success is going to be that we get a red. And the number of trials has also changed. The number of successes now, there were 4 reds. That's going to be 4. There's still 15 candies in there. And X is, well, we don't know how many successes. This is not a probability question. This is what we're trying to find. This is what we're trying to find. So we're going to be using a different formula here. The formula we're going to be using is we want the expectation formula. So the expectation formula is going to be NA over T, which is going to be 3 times 4 over 15, which is 0.8. And that's not percentage. So it's very tempting to look at the 0.8 and turn to percentage, but this is not a probability calculation. This is an expectation question. So the question is, how many do we expect to get? The answer is, we expect to get 0.8 red candies. Will we actually ever get 0.8 red candies? We will not, but that is what we expect to get when we do this once. When we pull 3 candies, we expect to get 0.8 of a red candy. We could do it with an XPX table, should I? What we could have done so if we wanted to have an alternate solution, so you could convince yourself that this kind of works. So it's x p of x, x p of x. So we pulled 3 marbles from the box, so we could have had 0, 1, 2, or 3 successes. The probability of getting 3 successes was we had 4 reds and we wanted to get 3 of them. And of the 11 non-successes, we wanted to get 0 over 15 choose 3. And then this would be 4 choose 2 times 11 choose 1 over 15 choose 3. And this would be 4 choose 1 times 11 choose 2, because we want 1 red and 2 non-reds. Or you could do it with the hypergeometric way as well. Or 15 choose 3. And this one is whatever, we don't know. So the XPX is going to be, that's 0. This is going to be my calculator. So 4 choose 1 times 11 choose 2. Oops. 11 choose 2. Divided by 15 choose 3. So that's going to be 0.48. 4 choose 2 times 11 equals divided by 15 choose 3. Wait, did I do that right? 4 choose 2 times 11 choose 1. 4 choose 2 times 11 choose 1 equals divided by 15 choose 3. So that's 0.15. And then 4 choose 3 times 11 choose 0 equals divided by 15 choose 3. And then 0.01. Well, that's not going to work. Okay. Well, we'll leave this on a pause for now. If somebody could figure out what I did wrong over here and let me know, that would be wonderful. But we'll move on, because that should have come out to roughly the same. I'm not sure why it didn't. So, over here, oh, because I know why. Because it's 2 times that. So 4 choose 2 times 11 divided by 15 choose 3 times 2. So that should actually be 0.29. And then 4 choose 3 times 11 choose 0 divided by 15 choose 3 times 3. And that's going to be 0.03. And if we add these guys up now, we're going to get 0.48 plus 0.29 plus 0.03, which is 0.8. And everything is good with the world once again. Okay, I feel a lot better now. Yes, it's important in the XPX tables to multiply by the x value. That's a critical part of the whole XPX table. D. The probability that x equals 0. I didn't ask a question. D. What is the probability you will grab at most? I'm running off the page right there. D. What is the probability you will grab at most? Remember, that's a key word. 1 blue if you grab 7 candies. So what's going to happen there is, if we're going to want to get at most 1 blue, success is going to be blue, and then the number of trials is going to be 7. The number of successes is, how many blues are there? There are 5 blues. There's still a total of 15 things in here, and the number of successes we're looking for are 0 or 1. So what that means is we're going to have to find the probability that x equals 0, and we're going to have to find the probability that x equals 1. So it's going to be 5 choose 1 times 10 choose 6 over 15 choose 7. This is going to be 5 choose 0 times 10 choose 7 over 15 choose 7. And you would get those 2 answers. You would add them up. And then that would be the actual probability of getting at most 1 red candy. And that's it for expectation.